so if anyone has any questions to start off, I've got like 13 people watching at the moment, so we might as well start. Um, Anywhere else? Oh, need some help with almost everything. Yeah, these questions this Tute were a little bit harder. They're a bit more conceptual than usual. Um, but is there any particular one you would like me to start with? Okay, Maxwell's Demon. So, essentially, what you have is. Let me go to the pen. Essentially, what you have. Um, is you've got the inside of the nucleus, a membrane, a pore, and the outside. And so what happens is you've got some carrier that can pass through both ways, and you've got some sort of cargo on the inside or the outside. And so let's label that like this. But the cargo can't go through by itself. And so when it attaches to the carrier, it can then diffuse through here and then end up on this side. And you have some other accessory protein which can split these apart, so you end up with the carrier and this. And so on this side of the membrane, you end up with the cargo that cannot anymore go back. And so what you have is you have this demon that is sorting, you're sorting this cargo across a membrane, and so you're building up a gradient that way. And so in a sense, the demon is the thing that unbinds the cargo from the carrier, and the thing that binds the cargo to the carrier over here. And so that's what's allowing it to sort. Does that make some sense? It's not a Maxwell's demon like it's sorting hot and cold particles, if that makes any sense, like fast and slow particles, but it's more sorting particles just generally. So you're making a concentration gradient instead of a temperature gradient. Is there any questions about that? Anything you want me to go through again? I know it's a bit biological, so it's a bit sort of out of a lot of people's realm, but it's kind of interesting. Alright, so if there's no questions about the demon one, I will now just go to question 2. Question 2 is about how information is essentially conserved in quantum mechanics. If you had a particle in, let's say, it could be in a superposition of a number of different states, then the information there is conserved because it always has to select one of the states, if that makes sense. So as it evolves in time, the particle just doesn't disappear. That's essentially what we're saying. And so it sort of operates similar to Liouville's theorem, which is that equal areas of phase space are conserved because that's how it's sort of like your probabilities are conserved in your phase space. And it also ties into a big open question in black hole thermodynamics, which is basically that black holes eat information and we don't know where it goes. So that's kind of what I was trying to get at, more conceptually, that in quantum mechanical systems, it's always going to select a state that's conserving information, and that's about it. There are also heaps of really good threads on physics stack exchange that also go through some of these questions as well. All right, did you have any questions about that? Anything specific? And the sound didn't cut out when I went to the drawing screen, did it? Either? Is that okay? Cool. Good to know. All right. Cool. All right. Next question. Does anyone have anything in particular that they want me to go through? Anything that someone's gone through a bit of but can't quite get all the way? Sure. Question 8. All right. I'm only going to do the non-extension bits because the extension bits are actually very hard, and it was just for if anyone wanted to give them a go. So for an ideal gas, you have U is equal to F onto NKT, and PV is equal to NKT. And this is also equal to F onto PV. So the enthalpy, H, is equal to U plus PV. And so if we go to the infinitesimals, we have du plus dPV. And then we can plug in F onto NK dt and NK dt, because that's just coming from that there, and that's coming from that definition. And then we end up with F plus 2 on 2 NK dt. And so we end up with an enthalpy that's equal to H naught plus F on 2 NKT. Is everyone happy with that so far? This is also equal to the specific heat at constant pressure. Anyone want me to go through anything in particular there? If not, I'll just move on. Cool. So, to calculate the, so firstly, Stirling cycle, we have PV diagram, which is C, B, A, and so the enthalpy, or D enthalpy, is equal to TDS plus VDP. And so let's just calculate these changes for each leg of the cycle. So the change in enthalpy for the adiabatic leg is going to be equal to the integral of V dP. And because it's adiabatic, we know that PV gamma is equal to some constant. And then we can substitute that in. So that implies that we have A to the 1 on gamma dP, P to the 1 on gamma. And then you can integrate that and you get there. What am I doing? -1 plus gamma 1, sorry. Pretty sure that's right. And then when you substitute in the adiabatic equation there, you should end up with F and I got this because gamma is equal to F plus 2 on F. And so you just substitute those in and substitute V in. And that is also equal to F plus 2 on 2 NK delta T for the adiabatic. Alright, so we'll come back to this equation in a second. The next thing we want to do is calculate the change in enthalpy for the constant volume process, and that's just going to equal F on 2 on 2 P dV plus V dP. That there comes from the fact that H is equal to H is equal to H naught plus F plus 2 on 2 and K delta T. Well, actually no, not delta T, just T. And that can be substituted for PV. And so if you take the total derivative dH, you'll end up with F plus 2 on 2 PdV plus VdP. And so when you integrate this equation, this is now aside, you end up with F plus 2 on 2 V delta P, and because it's a constant volume process, we actually end up with F plus 2 on 2 and K delta T. So this is going to be another equation we just put aside. Can I scroll? No, I can't. And now we will do for the constant pressure process, dP is equal to 0. And we basically do exactly the same procedure. So we've got F plus 2 on 2 P dV plus V dP, and that's going to be equal to F plus 2 on 2 P delta V, which is equal to F plus 2 on 2 and K delta T. Alright, so we now have all of our changes in enthalpy for each leg of the cycle, and we'll put this equation aside as well, and we just need to now put everything together. So I got all of my changes in entropy just from the equations that we know from the lectures, which we've already derived before in class anyway. So we've got the change in entropy for an adiabatic cycle is equal to 0 just by definition. Change in entropy for a constant volume process is equal to F on 2 n log T final on T initial. And the entropy change for a constant pressure process is equal to F plus 2 on 2, oh that should have a K there, log T final on T initial. Alright, and then we also have our changes in enthalpy. So dH for the adiabatic process is going to be equal to F plus 2 on 2 and K delta T. Change in enthalpy for a constant volume process is equal to F plus 2 on 2 and K delta T. And the same here. And you'll notice that they're all the same, mainly just because that the enthalpy is defined off the temperature, and so it only depends on that state variable. So we can always just define it as such anyway. So we have enthalpy up here, entropy here, and let's compare that with the PV diagram, which is this. So we're going to have a constant entropy process going from C to A, where the it's going to have a lower temperature at the end. So we'll end up with a leg of the process that's going to be like this. It's going to go down from C to A. And we also have both of our enthalpy and entropy parameterized by temperature. And so what you have is these logs just here. And so if you do plotting the log on the h-axis, then you end up with a sort of log like that, and then another one like that. And so the steeper curve is the constant pressure process. Wait, hold on. Constant volume process. That's not right. Yeah. Going the other way. No, that's fine. All right. So you have it going around this way. So you have two logs that have different gradients there, and that's it. You also notice that h could also just be substituted for t, and so you can just do it like that anyway. Or you have a TS diagram, and so it's just a different parameterization of that as well. Except I went around the long way. All right. So that's that. Is there any questions about that very long and tedious calculation? So, what's the next question you guys would like me to tackle? We also have the two different tutes as well. We have the one from Paul's part and the one from Tim's part as well. And so you can draw from both of those. Can you do some of Tim's question, please? Sure. Okay, let's do question 1. Let me just get that up. But how do enthalpy? Yeah, they're mathematical conveniences in a way, because often in chemistry you'll use enthalpy because you want to calculate heat and entropy changes, especially during phase transitions and during what else? And during chemical reactions. Gibbs free energy is used a lot in like biological systems because you're looking at things where temperature and pressure are held constant because it's just in a room, in a cell, but you're changing the number of particles and things like that. And so you just use them when you need those sorts of parameterizations where like pressure or temperature are constant. And so they're just for convenience, I guess. But you are sort of calculating a real quantity you can compare with other real quantities. And I think that is the key there, because you're just looking at a comparison of a different parameter for each system. So that's why it's sometimes useful. Does that make sense? All right. 3A is easier than 3B. So let's just check that you've gotten 3A. So we have total energy of your system is going to be equal to the total kinetic energy plus the total potential energy. And so the virial theorem basically says that for any power law potential, you have this here, where the potential is 1 on Rn. And so this then gives us for sorry, that's not right. That should be R to the n. So this, for n is equal to -1, that means that our potential energy is going to be equal to, that should be K as well. Okay, potential energy is going to be equal to 2 times the kinetic energy with a minus. And so what we end up with is that the total energy is equal to minus KE by just substituting in the top. Oh, thanks for that. And so by equipartition theorem, we know that each degree of freedom is going to contribute to the energy by an nkt. So we've got the kinetic energy total, which is essentially the internal energy, sort of. Actually, hold on. So our kinetic energy, because it's 3 degrees of freedom, we have F on 2 nkt. And so then our total internal energy, which is just equal to our average total energy, is equal to minus F on 2 nkt. And so by the definition of the heat capacity, you end up with du dt, which is equal to minus F on 2 nk. And so the weird thing about the heat capacity here is that it's negative. So if you increase the temperature, you decrease the internal energy, which makes sense for orbital and gravitational systems, because if you make things go faster, they tend to go closer inward, and so they'll be spinning faster in a tighter orbit. And so for the second part, we're going to have, we use this equation that I had before, minus C n squared on R. So this is some sort of system average R. And the radius is proportional to V to the 1 on 3. And so that means we're going to end up with something that is like C dash n squared on V to the 1 on 3. And then we also now use the virial theorem again, which is that the kinetic energy is equal to minus a half potential energy. And so knowing that this is F on 2 nkt, we then say we've got F on 2 and kt is equal to minus a half outside of minus C dash on V. Those cancel, minuses cancel, ends cancel, and we end up with, let's lump all of our constants together. So we've got f k on c dash is equal to t, times t is equal to n on v cubed. So now we have an equation of state. We also notice that it's independent of pressure, which is a bit weird. And so the next thing I said in the Tute problem was that you can substitute this into the ideal gas just for a good approximation, because the volume term here is sort of a substitute for the configurational term generally. And so as an approximation, we can say that because we have an volume, number of particles, and temperature, just from the calculation we've done many times, is going to be some offset plus nk to the 3 on 2 natural log of t plus the natural log of v on n, and we have entropy there. And then if we just plug in our temperature from before, so temperature being c dash on fk, then n on v, so then that's equal to nk half log of v. Alright, and so that's what we end up with. So as the volume decreases, the entropy decreases, which is kind of what we expect. Alright, so that's the end of that, and we're about at the end of the hour. Is there any final questions that you have before we finish up? Yeah, and I'll go through Tim's question again, and I'll redo that one as well. And also for those of you who are still watching, how did this go? What are your views on how we're doing things using the YouTube live stream? Did it work for you? Is it okay? How else? How else do you think do you want to run it? Because I was kind of thinking that because we don't have a defined class time anymore, because it have to be in class, we can split it across Monday and Friday. So as in, we'll do one for, let's say, the week 5 Tute, it would be Friday 30 minutes roundabout now, and then Monday the week after, like after the weekend, so you can catch up on work or whatever, and at some time then do another 30 minutes. What do you think? Okay. Cool. All right. It won't start this if we do the split, and I'll post about it if we do. It won't start next Monday, so it won't start in 3 days. It will start the week after, and I'll post. Maybe I'll post a schedule or something like that about when I'll come on just to answer questions, if that's okay. Because I figured then it's more flexible for people as well.
Easy. So, I guess we're at the end of the hour, so I'll just be signing off now. So, thanks, guys.